right. So last time we talked about wastewater, why we care about wastewater, all that stuff. Today we're going to talk about the secondary treatment component of wastewater treatment. This is after we've done a little bit of sedimentation and kind of done the just generic basic screening of large stuff out of the water. Then we're going to use essentially biological activity as best we can. That's the whole goal of secondary treatment. Grow a bunch of microbes, catch them. It's easier to catch the microbes than the dissolved organic stuff. So when we think about a typical secondary treatment process, we're taking what we would call primary effluent. So in your mind, as you think about what we're doing in a process, so if we encounter a word problem that says we've got primary effluent, what that's referring to is this is water that's coming out of a primary treatment step. And then that would also be called secondary influent, right? We could say secondary influent is equal to primary effluent, right? So you'll see that, and just keep that in mind because that can be a little tricky sometimes. So we have some sort of primary treatment. It takes care of some stuff, and then we get down to business with the bacteria and say, we're going to take the effluent from that stage and we'll draw a control boundary around the aeration tank and the clarifier, and that's what we're dealing with for our secondary treatment. So or at least the biological aspects of it. So this aeration tank is really the driver of the activity. We're basically bubbling oxygen. Sometimes we even add extra oxygen, more so than just as in the environment. It costs a little extra, but sometimes you can get better activity there that way. And essentially we are activating the bacteria here and causing them to grow, giving them every chance we can to eat food, to multiply, reproduce, and ultimately form cells that are going to fall into the clarifier, fall to the bottom of it, and be collected as a sludge. So then we call this a waste-activated sludge. We could say a waste-activated sludge line when we collect it. So we'll call it waste-activated, spell correctly, sludge. That's WAS. And we could even call the primary aeration tank a WAS tank. That's how people will call it, the WAS line to waste activated sludge line. This is activated sludge. It's an aeration tank, activated sludge basin. Basically just creating as much oxygen-driven biological activity as we can so that doesn't happen in the environment when we discharge the water. We'll have a recycle line or recycled activated sludge, RAS. We'll have an effluent from the clarifier, and we'll have some sludge that is taken and not recycled, and that's sent out to our biosolids processing or our landfill. So that's kind of the essence of it. We have two outputs and one input, right? In this system, we have the primary effluent coming in as an influent, and then we have the secondary effluent going out that's primarily water. Then we have this WAS line that has a little bit of water, but mostly it's sludge, right? So it is liquid, but it's mostly sludge-like stuff. So it's pretty concentrated bacteria junk. So that's the system. If we were to look just at the aeration tank itself, we would see we have one input and one output, right? Like a lot of our systems. So as we go through, today we're going to focus in on just the biological activity that's happening inside the tank. So we have a good understanding of how the math works to understand what's going to happen to the waste itself, which is bacteria food, and to the bacteria themselves, which is our workers there. So next lecture, we're going to go over some sort of like shortcuts to understand how to balance these systems, assuming they're at steady state, assuming things are operating well. how we can manage them sort of on a bulk front. Today, we're going to dig into the mass balance of how the bacteria is thriving, surviving, and doing all its stuff inside the tank itself. So that'll give us better context for the kind of slightly bigger picture stuff. Okay, first, some terminology. When we talk about, I already mentioned this waste-activated sludge. That's this slurry of microbes. Seems pretty gross, right? The point here is it's constantly aerated. There are systems that deprive the bacteria of oxygen. We can get a whole separate biochemistry, different degradation stuff. Sometimes those are used, but in a typical secondary treatment, we'll use a activated sludge where we have aeration providing both air and mixing. So it'll give them the oxygen. We'll end up mixing the system rather completely. So we're typically dealing with a CSDR. So water flowing in, very well mixed, water flowing out. Okay, then we have wastewater strength is a term that you'll see used sometimes. This is really referring to how much organic matter there is there, how much biodegradable organic matter. So BOD is a biological oxygen demand. How much oxygen will bacteria use because of the food that is available? That's what we're measuring. We're measuring the food in terms of oxygen. Okay, it's kind of a weird thing, but that's the deal here. Typically, our wastewater strength will be somewhere between 50 to 60 milligrams BOD per liter, up to about 500 milligrams per BOD per liter. Those are kind of typical values. If you get below this, then perhaps why even treat it as wastewater? Your bacteria might not grow particularly well. Maybe there's other cheaper treatments that you could just do in order to clean up the water. Above that, I think is just pretty atypical to see it. Certainly possible, and perhaps you could design a system specifically for really high BOD cases, but generally that's the upper region where we see for municipal treatment plants. Another important term is volatile suspended solids. This is going to give us a way to weigh our microbes. It's kind of a crude method, but it works because we're dealing with so many microbes that it's okay. We can use this crude technique. We'll say this VSS. Oops, not W. This VSS technique is crude in terms of we're not actually weighing microbes specifically, but really it is quite effective for wastewater. We wouldn't do this with trying to figure out how many bacteria are sitting in here in my water bottle. We would do it for the case where we have this sludge. And so the process here is we take a typical total suspended solids filter. I might not know what that is, but it's a filter that's going to capture anything above some size, probably 0.22 micrometers or something. Basically capturing anything that happened to be suspended in water, but it's not dissolved. Right? It's some solid particle, something that will be caught by a filter. So we filter it, and then we dry it. We dry it at about 100 degrees Celsius, or maybe just over, so that we're not burning stuff, we're just drying it out completely. There's no more water there. So then we weigh that. That's our total suspended solids. A subset of that is this volatile suspended solids, because once we dry it and we have the weight, we know that's some mass of stuff that was in the water suspended, and we call it solids because it was not dissolved, stopped by the filter. Then we heat it at 500 degrees Celsius, so quite hot, burn off anything that we can, volatilize it into stuff like CO2 gas, probably nitrogen gas, whatever other gases are associated with the compounds there. These two would be the primary ones. And after that, we weigh it again. So we've lost a lot of mass by burning, right? We've volatilized it, burned it off. Then we weigh it again, And that difference, we'll say, is the mass of bacteria, because all those bacteria are predominantly just organic matter. And so when they were burned away, that organic matter disappeared, and what's left is just some ash, mineral stuff, probably not so much bacterial related. There's going to be maybe a few very, very micronutrient levels of minerals in a bacteria cell. Sure, there's some enzymes that use different metals and things, but it's very, very small amount. So most of it's going to be caught by this. So that's why it's crude. But when we're talking about grams of this in every liter, it's pretty effective, right? We can get a good estimate of how much bacteria we have with this technique. So we'll see this in a variety of places, and we'll use this to describe the amount of bacteria. So if I flip back for a moment, inside our aeration tank, I didn't note this yet, but we have V for the volume, then we have X and S. So in most of our systems, when we draw them up, we say, okay, there's some volume, maybe some reaction, yada, yada. Usually put some sort of concentration or some number or something. Here we have X and S. So X being the microbe concentration. And I have this all written out well later, just kind of noting it here. And S is going to be substrate or food. So I'm going to use those two terms pretty much interchangeably. A substrate for the bacteria to grow on is their food, right? So S then is kind of the wastewater stuff that we're trying to remove. That's the BOD. Okay, so then this VSS, this is going to be effectively our value for X. And it's going to be in milligrams VSS per liter. That's our microbe concentration. Okay, so that'll be a handy way to deal with the microbes in a mass sense. So as we see, yet again, we're taking some sciencey sort of concept like biology, microbiology, and all the processes involved, and we're just kind of distilling it down to how can we use this and design it on a mass or number basis and engineer it, right? So a little bit more about that. A typical secondary treatment step is going to remove something like 95 to 98% of the BOD. So let's say in the worst case, we started with 500 milligrams of BOD per liter, and we take through the secondary process. Let's say it does 95, then that can be down to 25 milligrams BOD per liter, for example. Right? So at 25 milligrams BOD per liter, one thing we can consider is the fact that in a sample of water, the saturation point of oxygen is about 8 to 10 milligrams per liter. Depends on the temperature a bit. But we can expect something like that. And so if we were to just take this treated wastewater now that has 25 milligrams per liter BOD and just let it sit there, whatever biological activity exists there will deprive it then of oxygen. It'll remove all 10 milligrams per liter of oxygen and have more waste left over. So if we think about it in that term, with that regard, this 500 milligrams per liter BOD, that's kind of the upper level of treatment or upper level of wastewater strength that we see. Taking it through a typical process, it's not quite sufficient. It's close, but it's not quite. So then we also want to think about, well, what is the receiving water that we're discharging to? So if we're discharging this into the Mississippi River, obviously it's going to be quite diluted. And so the river itself might not really even see an impact hardly at all, especially if this was a small flow of wastewater. Now, if it was a large flow of wastewater into a small stream, that's going to be a much bigger deal, right? So there's some context that matters there in terms of the actual impact it's going to have. We're going to talk more about that in a few lectures when we get to the BOD downstream lectures. So anyway, that's a little bit of context, a little bit of food for thought there. Another thing I wanted to mention here is that when we talk about BOD, that's mostly carbon type food that we're talking about. If you were to look at a sugar molecule, sugar would definitely be a source of BOD. It's going to be mostly carbon and hydrogen. That's basically most of what a sugar molecule is. Most of the BOD we're talking about relates to the carbon itself. That doesn't give us the whole picture, though. I think I mentioned this last time, because microbes also need some amount of nitrogen and phosphorus. So it turns out if you take a tissue recycling plant, taking all sorts of fiber from cardboard, from paper, things like that, and I had a chance to tour one of these as a permit writer in Michigan. It was very interesting. And they had a wastewater treatment plant because they were processing a lot of this fiber in water. And so essentially they would break the stuff down, use some chemicals to help dissolve sort of, or break apart the cardboard and stuff. Mechanically, it was almost like they had a stomach, but it was a reactor, right? It was like they put in, I don't remember if it was acid or maybe it was straight up bleach or something, in a mechanical tearing, mixing sort of a situation, process a lot of it, and then downstream, they would be harvesting the fibrous materials out of it, trying to gather anything that was fibrous. So they were collecting all those fibers. They were ultimately going to make it into like a paper towel and toilet paper products. But that left the water with a lot of organic, but mostly carbon-based stuff. If you think about paper, there's going to be some mineral stuff in it, but there's mostly going to be this sort of a carbon. It's like wood, right? It's mostly built in that carbon. So it's a lot of carbon and not a whole lot of nitrogen or phosphorus. Whereas if we're eating food and excreting food and sending that down the toilet and all that, there's a lot more nutrients in addition to the carbon. So at any rate, they had to actually fertilize their bacteria because they had plenty of carbon that they wanted the bacteria to eat, but then they had to add nitrogen and ammonia. So they literally just bought fertilizer from, agriculture supply and would just pour it in. They'd just be like, okay, this needs a 5-gallon thing every hour or whatever. It's like they just pour it into their bioreactor because they had enough food. So this is an important concept in several fields, particularly microbiological related. The CNP ratio, if the bacteria need, and typically they will need about 100 times more carbon than they need phosphorus. So you could say, phosphorus is limiting if they have a whole bunch of carbon, but like absolutely no phosphorus. Or maybe carbon is limiting, right? So in our municipal wastewater, typically there's lots of carbon and lots of phosphorus and nitrogen, and then the BOD is the remaining carbon. This is, by the way, used in, let's say, like oceanography and things like that. The Redfield ratio is for algae. That's a similar one. I think that's 100 to 5 to 1, maybe. I can't remember exactly. It might be 7. So you'll see this in different places, and you could measure any biological life in that manner. You could say humans have such and such a CNP ratio if you were to, take the remains and process to figure out the atomic composition. So that concept here is kind of important to see. Okay, what are the actual nutrient requirements there? Typically, for municipalities, it'll be mostly carbon that we're paying attention to. All right, so I have a quick video that kind of gives a decent overview showing of a wastewater treatment plant with some music. So there's no words or anything here, but right here, I believe they've got this on the right is the primary clarifier. So they're just sending water through this long basin. It's fairly calm, flowing through it. Whatever is large particle, you can actually see the activated sludge. We'll focus in on that in a minute on the left. So water is just making its way through. It's quiescent, laminar flow. They're harvesting water across the top. Sludge will accumulate along the bottom, and they'll take that away over time. So you see it's spilling over that top. So that's probably the primary effluent there we're looking at. It's going to head over into the secondary treatment step. And you see it's pretty nasty looking. So then it makes its way over to here. Then we have our aeration tanks. Seems to me like these are probably 3 tanks each in parallel. I'm not positive about that. Could be doing something different. But you see quite a lot of bubbles. There's continuously aerating. That's the activation there. And I mean, if it wasn't already obvious, you really don't want to fall in here, because if you were to fall in here, you're not going to be able to swim, because you're not going to have any buoyancy, because there's mostly bubbles, right? This is the reason why, if you're ever on a sinking ship of any significant size, you want to swim away from it as fast as you can, because you would sink from all the bubbles that are coming up around you. So the same principle applies here. So if you do ever visit a wastewater treatment plant and fall into their waste activated sludge system, make sure you know where the ladder is. That's their safety protocol. You have to be able to walk over to the ladder and climb out. Yeah.
How deep are these?
It depends a bit. I think they're usually 15 feet, 20 feet, something like that.
You're supposed to walk?
There wasn't one of the tanks. That's all.
Yeah.
If you scoots back a little bit on the video, you can see the ladder.
Oh, that's fine.
Where is it? Do you see it?
One more tank back.
They should have ladders, and it may
No, it's just pipe.
right in the corner. You say?
It's either a pipe or a ladder. I'm hoping that's a ladder.
Now
It's a pipe.
maybe, yeah. So I don't know. Maybe they have alternate systems, or maybe there's like shelving on each thing, so you could at least make your way most of the way. I don't know. I'm sure there's more safety protocols.
How would that work?
This is also not in the. This plant is not in the U.S. there,
The
so
life preserver would just sink them, right? Like, could you,
it might help a little,
Kinda like
but
lasso
probably
the
not
person
much.
in.
Yeah. Lasso them and pull them back out, right?
Right.
Yeah. So, I think that if there's ever any maintenance issues where somebody would actually have to risk, be at risk, I think they do harnesses and stuff. Yeah. So that's a kind of a crazy thought, right? That's
Yeah.
You thought it was awful at first until I went and told you that. All right. So then from there, I think we're taking that, and this right here is probably that secondary clarifier. You see a lot of foam scum accumulation along the top, so they're not going to take directly off the top. It's pretty typical after you've given it so many bubbles. It's going to have some of that. And then, not actually sure about this, but that might be a disinfectant contact chamber, or it might just be, I don't know why they'd have little windows like that. But from there, it's heading out, and I think they're probably discharging after that point, and you can see at that point, the water actually does look a lot better. So it's kind of impressive that it cleaned up that well, I suppose. And I think they show.
What makes
Yeah,
it
there you go.
necessary to see it, I guess.
What's that?
What makes it necessary? What's the value of sunlight? I'm assuming everything has a purpose. Like, to get any cultures going, or like?
For the sunlight, just that it's open to the environment, is what you're saying, or what?
Yeah.
Usually it's just cheapest that way. Some systems could have
Plus, it's probably easy to identify where an issue happens. So.
yeah, so problem identification. Yeah, and so one of the things we'll talk about a little bit next time, I think, is you want to keep your bacteria happy. Ties in a little bit to the CNP ratio stuff. If you give them the wrong type of food, you might get the wrong type of bacteria growing. So let's say bacteria that like to eat fats and lipids that you might find from like a restaurant wastewater or something, or something like that. Some of them can then form a bunch of filaments and start floating. And so you saw that scum layer there, which is kind of expected. But if it becomes excessive and most of the bacterial mass floats because they're making funny filament things, you have all your sludge float and escape your clarifier. That's bad news. Lots of bad things will happen because of that, because in part then we're not recycling appropriately. We're no longer managing the concentration of bacteria the way we designed it for. So we'll see that as we move forward with some of the I'm going to take a quick step back. When we consider this graph, it turns out that this waste activated sludge line that takes that bacteria that has been clarified, controlling that one parameter turns out to be very important to the effectiveness of the whole system, because it's controlling how long the bacteria stay in the system. Because we can increase or decrease that, and that will automatically increase or decrease the recycle and all that. So it becomes very important mathematically to have good control of that. And so normally we assume that our XE here should be close to zero, at least on this bulk mass basis. There's going to be bacteria getting out, of course, but like on that mass of stuff. So that's a good question, and it becomes very important to watch for that kind of stuff.
I have 2 questions.
Yeah.
One, all of that water that was like quote unquote clean, but still like green looking.
Yeah.
Where is that going?
So that water that looked clearer, but certainly still had contamination in it. I don't know where that plant was sending it, but that might be the end of their treatment, and then they send that to whatever receiving water was nearby. So that could just go straight into a lake or river. If you notice, there was some signage there. I think it was Spanish, so certainly wasn't in the U.S., that plant. So it would depend on the local regulations. But yeah, that if it did not go straight into the environment from there, they'd probably do a disinfectant step or possibly tertiary treatment to remove more nutrients. But I think they would have done that before doing the clarifier, or before. Well, I don't know. Maybe they could perhaps seed another set and do all that, but it would look something like that when it goes out to the environment.
And then my second question was that like all of the stuff that's being cleaned from the water, where is that going?
Yeah, so once we take all that stuff, it depends a little bit on what you want to do with it, because there's typically a lot of nutrients there that could be recycled. So you can take the sludge here that you decide to send to waste. Either way, you're going to dewater it, so you're going to squeeze out the nasty juices. That'll just be sent back into the beginning of the wastewater treatment plant. You could then send it to kind of a compost process. If you get the right temperatures, it kind of helps with pathogen control. Then you can repurpose that as biosolids for land application, kind of fertilizer. So it's basically composting. We have some concerns of heavy metals in that, so we don't want to overload it. Otherwise, it's just going to go to a landfill. And so then the landfill presumably protects the rest of the environment from any issues from that leaching out into it. But it's almost like you're adding soil into a landfill in some sense. Yeah. Great. Okay, so now that we kind of have that big picture view of what's going on, we need to know something about the actual growth of the bacteria, because that's going to tell us something about the removal of the waste, the substrate stuff. So that brings us to typical growth kinetics for microbes. This is, we have an equation called the Monod equation that tells us something about how quickly bacteria will grow given some amount of food. So this is going to be a lot like our flocculation reaction equation that said the rate at which the particles are going to meet and stick together depends on all these things, right? The rate at which the microbes are going to grow depends on, first, the amount they grow, or the rate at which they grow when they're super, super happy and have as much food as they could possibly want. That's the mu s. So mu s here is the maximum specific growth rate coefficient. You see that's per time, so this is a first order growth constant. We know it's growth because we're dealing with growth. We know it's first order because it's time, and this is when they are super happy microbes. This is a super technical term. They're living their best lives, eating, reproducing, all of that. Okay, so then mu here is the specific growth rate coefficient given the current circumstances. You know, maybe they're starving and not so happy. This is just dealing with whatever happens to be their current state, given their current environment. So mu itself, this is going to go into an equation that's like this. We would have dx dt would be, it was a growth equation. It would depend on x and mu, right? Just like we've done in a lot of cases. That's where this mu is going. Okay, so then it also depends on the S. We said S is the substrate concentration. That is essentially the amount of bacterial food. How happy, you know, how much food they have will determine how quickly they can grow and multiply. Then we divide it by the amount of food there plus this other constant, this Ks. There's going to be several Ks. I apologize. I'm just going to follow the book's nomenclature. This is an uppercase K with a subscript S. That'll be distinct from a couple other ones we see. This is called the half velocity constant. And on the bottom, we see we have S in milligrams BOD per liter plus this. So this also has to be some measurement of milligrams of BOD per liter. And essentially what this is the amount of food when the microbes are halfway happy. They're halfway to their little nirvanas or whatever you want to say. So I'm just going to write 1/2 happy because that's funny, right? Essentially, the amount of food that gives them half of their maximum growth rate. So I'm going to show you in the next slide a picture of that. But real quick, X here is the microbe concentration, milligrams VSS per liter. S is the food or substrate concentration, milligrams BOD per liter. And it looks like I have S twice, so I don't know why. Who cares? So that's the situation. All these different parameters there. If you do get any confusion with the Ks or the different terms, you'll have all of these right here for you. Okay, so just to take a quick look at that Ks value here, if we want to describe how to find this Ks, well, we can think about, if we take a look at the graph of the rate constant for growth, so per time unit here, at maximum, we have mu max, right? So we'll start at 0, we'll reach mu max at some point when we have lots and lots of food. And if we think about it, you know, it'll probably be approaching this like an asymptote, right? If you look at the equation, it'll kind of show you that's what it should look like. When we have no food at all, they're not going to grow. Should be pretty obvious. So we'll start down here. And then it'll look something like this, where eventually we reach mu max. And at some point, we have half of that, right? So 1/2 mu max should, let's say, be right there. And to find that Ks value, what we're doing is we're saying, okay, well, how much food is required to reach that? And that then is our Ks. So that's just a little picture of where that Ks is coming from. S is, of course, the current amount of food they have. And mu max is like, well, what happened when we gave them as much food as we possibly could give them, right? So that's the different parameters here. I'm just showing you that so that you can kind of understand what's going into this mu. It's a function of how well they grow at max, with some caveat of like, well, where are we compared to halfway there? So it doesn't matter too much. I'm not interested in deriving it all, but that's the monod equation. Those are the parameters that go into it. The uppercase Ks is the is the one that's in BOD per liter units. Okay, so with that, I'd like to talk a little bit about what happens if we put it in a bottle and say go, right? So we put some initial concentration of X, we spike it with some bacteria. We could call that, in this case, we'll use colony forming units per milliliter, because if we're doing like a little culture test, we're typically measuring like in a lab and just specific numbers. So we'll check that in this case, and we can plot how many there are, the CFU per liter, or milliliter rather. We'll put that on a log plot. So log of X here, so this, we'd start at 0, we go to like 10, 100, and so on. And so if we plot that over time, we can see that what's going to happen is, and let's say this is probably hours, if we're saying that this would typically be something like 24 hours for that, around that time frame. So for the first few hours, we have a lag phase. Nothing really interesting happens. That's typically about 4 hours, 3 to 4 hours. Nothing really happens. The bacteria have a new environment. They don't know what's going on. They start realizing, oh, there's some food here. Maybe I should, change my clothes and get ready to go out into the town and eat everything, right? So that's kind of, the bacteria will, when they're, let's say, suspended in a refrigerator or something, they're going to kind of freeze up a little bit and say, okay, I'm just going to go in slow mode here and just survive. But then once they have an environment that's conducive to their growth and reproduction, and there's food, they start getting going. They may start signaling to one another and start growing rapidly. So this is why if you ever go to maybe a Sunday picnic or something, and there's a lot of food outside and left on the picnic table, let's say it has a lot of mayonnaise and possibly some raw egg in it somewhere, and lots of room for bacteria to be there. If you just put it out and it's been an hour sitting out, it's probably fine to eat. But if you leave it out there and you come back to it after playing some sports or something, 5 hours later, and then you shovel some into your mouth, might have been a bad idea, because now you're past that lag phase, and suddenly, you had 100 bacteria in there from the eggshell or whatever, and now suddenly. And by the way, if you ever thought about where eggs come from, it's the same hole that other stuff goes out for birds. It's prone to microbial contamination, let's say. So then suddenly, a few hours in, you're thousands of bacteria more. You're multiplying very quickly, and if there was some bacterial contamination, you have a problem there, right? Okay, so that's kind of how the bacteria work. If you're doing the Sunday picnic thing, then eat the food early rather than later, right? Or at least the stuff that looks like it would make for a good microbe home. All right, so anyway, after that lag phase, we accelerate. We get this growth phase. Pretty much they're growing. There's probably a few dying, but really it's the growth is way out competing the death. Eventually, typically, it'll depend a little bit on how much food was in there and all that kind of stuff. Eventually, you're going to hit a point where they're really only growing as much as they're dying. So we'll hit a stationary phase. There's still some food around, but they're really competing with one another. There's just not a lot. There's no net growth. I guess the bacteria have reached a steady state in that sense. Eventually, they consume enough food to the point where their death is outpacing the growth. Of course, bacteria are little cannibals, so they're going to eat their neighboring dead cells or whatever, make use of whatever they can. So there's still going to be some food for them, some growth. But on a whole, the total viable number, that's the log, the y-axis here is the log of the viable concentration. There's still going to be quite a lot of them. It's just they're trending downward, right? So you could see this if you ever did any microbial work in a lab or something. You take some culture, maybe you're storing it for a little while. Eventually that stock sort of decays and you have less and less bacteria there. Even if there's a lot of bacteria there, you can see that it's just declining over time. So they're in that death or decline phase. Okay, so in this, we see then that we have two equations at play, really three. One would be the removal of the substrate. So ds dt is removing, or is decreasing. So you're eating the food, right? So that's, in a wastewater sense, that's what we're looking to have happen. We want the ds dt to be negative, want to decrease the amount of food in there. Then we also have growth of dx dt, and eventually death, so that we could also add a / negative here. So growth and death of the bacteria. Of course, at first we just care about the growth, and in an engineered system for wastewater treatment, we're typically going to be promoting that growth because it's correlated with the removal of the substrate. So to put these things together, then we can take a look at our growth rate, dx dt. Like I said earlier, that's going to be equal to mu x. So very straightforward equation. This is a first order growth rate. It's as if we said dc dt. From the start of the class, we've done stuff like dc dt equals negative k c to the 1 power, right? Except this is going to be growth, so it's not a negative. And we're calling this x instead of c, and we're calling this mu instead of k, right? So very much alike, just showing you here very clearly that it's the same form. It's just a first order growth, so we have a positive. We're no longer using c or n or something, we're using x, and mu instead of k. Okay, so then we can describe that by saying r of g, so the rate of growth, is equal to mu x, and we can put in the equation for mu here, so that Monod equation, right? We can just put this right into here and say that's going to be x times this mu max s divided by ks plus s. So that gives us our rate of growth. So that's going to be the rate at which the bacteria are growing in our system. Then we have to have a way to convert from growing the bacteria to removing the food, right? So here we get to a yield coefficient that's kind of like, I don't know, if you had a bodybuilder that wanted to see how much body mass it could add per milkshake or per protein shake, you'd be looking at a yield coefficient, right? How much food do I have to eat in order to gain that much mass, right? So this is what we're looking at for the bacteria. How much food do we feed them per mass of bacteria we produce? Okay, so then we have this other k here, and actually I probably should go ahead and write this yield coefficient first. So yield coefficient is related to a new k, which is the maximum specific substrate utilization rate. So the maximum amount of food that the bacteria can eat when they're growing as fast as they can grow. So those three terms are related, right? The yield coefficient being the maximum growth, specific growth rate coefficient divided by the maximum specific substrate utilization rate. So here's where I was talking about this k. It's a lowercase, no subscript. That's the one the book is referring to, say k is the maximum specific substrate utilization rate coefficient. Okay, so that's going to be another one of these coefficients that's probably just given. It would be understood based on doing some experiments to see, okay, how quickly when we give them when we give them the ideal conditions where they are growing as fast as they possibly can, we could measure that ds dt here experimentally to find that, right? That would be something we can measure. Okay, so with that, we have a relationship now between the substrate use and the amount of bacteria growing. And so what we can do is say a rate of substrate utilization should be equal to the negative of the growth divided by that yield coefficient. So the yield coefficient, by the way, is going to be, the units are going to be milligrams VSS, so the amount of mass per the amount of food. So mass per food, right? If the units are mass per food, then that means to convert from the growth to the substrate utilization, we just need a negative and to divide by that mass per food. So we have the rate of substrate use is equal to the rate of growth divided by the mass per food. Okay, so that gives us a nice term that we can use and convert between the amount of food and the amount of microbes. Because that's ultimately what we want to do here, is be able to handle the amount of food and know that based on the amount of microbes we're using. So we have that equation, rate of substrate utilization, we have the rate of growth. Those two are related. Last thing we need is a rate of death, and that's going to be quite simple. Again, a very standard rate constant here, KD. This is going to be a negative KD x to the 1 power. That's our rate of death and decay for the microbes. That's going to be first order decay per time units. So that one's pretty simple. Again, this is another one we would simply measure during the death phase. Just say, okay, well, now that we've removed all the food, how quickly are they just sitting there dying, right? So to put all those together then, we could say, let's get a net growth rate. So is it the net change in X is positive for some time, maybe it's negative in other times. Well, how do we know that? Or how can we model that? That's going to be R prime of G, the net growth rate, is equal to the growth plus the death. Okay, so we can just say R prime of G then is equal to, and if we substitute, can make sense sometimes to substitute our substrate utilization to get that in terms of substrate instead of in terms of our other factors, plus this negative death. Okay, so we have now a net growth rate equation in the form of substrate utilization and bacterial death. Okay, so that can be handy in a few different cases. Of course, we could just leave it R of G plus R of D. We could leave it, for example, as mu max S over Ks plus S times X minus KD X. Right? We can leave it that way, or we can account for the substrate utilization. So whichever one we need. Okay, so I have an example problem I'd like to go over with you. And this one, I'm not actually expecting you to do the whole thing, but I'm going to give you a few minutes to think about it and think about how you would approach it and what challenges are you facing to approach it. So we'll take a look at the problem text in a moment, but real quick, we have a table of parameters that are given. So if you're curious about, if you need to know the units for these, the K, the mu max, the Ks, the Y, the KD, all of these are listed here with their units, the range of typical values for these different parameters. And it kind of gives you a sense of these parameters are sort of known or can be known about a system, right? So all of these parameters are just sort of features of bacteria, microbiological growth. Okay, so they also give us default values. So this problem is going to call on these default values to use them because it doesn't give the values directly. So these are types of things that I would give you most likely on a problem. So in this example, we have a shallow pond depicted here. It stays well mixed due to the wind and the steady flow through of a small creek. So we have a completely mixed system and a flow through on both sides. That means it's a CSDR, right? So that's something we can identify from the get-go. We have a volume here, an amount of X, amount of S, some influent, so this stream flowing through is a Q. We have 0 incoming bacteria. We do have bacteria in the pond, but effectively 0 mass of them in there. And then we have 95 milligrams per per liter of BOD coming in. So the pond then is, in a way, a treatment operation for that. Now, there's no recycle here, so it's going to be different than our waste-activated sludge system on that regard. But otherwise, it's going to be a pretty similar case to take a look at. So the question is going to ask us, what's the substrate concentration leaving, and what's the amount of bacteria in here leaving? So it's going to ask both of those here in a moment and give you kind of a starting point. So it says, if the microbes in the pond consume the inflowing biodegradable organic matter according to typical kinetics, determine the following. A, the BOD leaving the pond. B, essentially the BOD removal efficiency of the pond. C, the concentration of bacteria, the volatile suspended solids, leaving the pond. Okay, so the start of the solution says, okay, it's a CSTR, can be well mixed, and we assume it's steady state. And then it's saying, first, let's set up the mass balance. And I'm actually going to have you think about it just from here. Just spend 3 or 4 minutes thinking about this, and then I'll resume with you and be thinking about kind of, again, what challenges are here that we haven't seen before in CSDR problems. Be right back.
We have to isolate this using units. God. Basically, we'll straw the picture, right? That's what I was supposed to say first. We have something going in, then falling here with a constant exodus. And we've got outflow. So 2 is 50. X. So it's going to remain at constant volume, but what we're worried about is this new aspect of this.
Okay, so part A here is asking us to find the BOD leaving the pond. What are your first instincts here to solve for that? Yeah, we said it was basically a CSTR. Yeah. So mass balance on a CSTR. But what would that look like? We've got 0 equals Q what? QS, or QS not, QX.
Oh, like entering it. Oh, okay.
Yeah. So
So
what?
so we're gonna relate it that way. Q. Well, we're finding out BOD, so we're gonna have to do. It can't be X plus anyway. That would make it equal 0.
Right. So there's a challenge here, right? Because as we're starting to think about it, what do we do our mass balance on when it depends on both X and S, right? X depends on how much substrate there is, and substrate's what we want to find, right?
Right.
So the point in part is that this is tricky. And it turns out that in this particular case where we have X coming in as 0 and it's a CSTR with no recycle, because if we recycled anything, then we'd have X not 0. So this particular case, we have a mass balance that works out in a funny way that if we do a mass balance on X first, then we get a term we can use for substrate. So we're going to do that. I'm not suggesting that you should have known to do this, but I did want you to think about this in terms of like, how are you approaching it, to see about that, to see if you could notice that. So a mass balance on X, if we start there, it would look like this, right? QX naught minus QX plus, here we have the net growth rate of X. So if we're doing a mass balance on X, we need in that volume R prime of G. So we'll expand that in a moment. So given that we have no X coming in, this becomes 0. And that means we have 0 equals negative QX plus the net growth rate in that volume. The net growth rate we said was RG minus RD, right? Or I guess plus, right? So the minus will be included. And so instead of just writing it out that way, I'm gonna just take those terms. So RG is going to be over here mu X. So that's going to be, I'll just say X times this mu value, which was mu max S divided by Ks plus S. Then we're going to add the decay, which is a negative KdX, right? So we've got that. From here, we might recognize that we can factor out an X from this term on the right, and we'll say, we'll just go ahead and actually move the QX over. So we say QX equals VX times mu max S divided by Ks plus S minus Kd. Okay, at this point, we can see a few things might cancel, including the X's. So we've done a mass balance on X, and the X's have dropped out. Again, that's specifically because this particular scenario, we have no X naught, and it just works out really nicely that way. So we can divide both sides by X. And if we divide both sides by Q, then we're going to be left with 1 equals V over Q theta times mu max S divided by Ks plus S minus Kd. From here, we just solve for S, and it's, a little bit of algebra. We have to multiply both sides and stuff like that, right? So we could say 1 equals theta times mu max s divided by ks plus s minus theta kd. So we add theta kd to both sides. 1 plus theta kd equals theta mu max s divided by ks plus s. So now from here we need to multiply both sides by ks plus s. Then we multiply that across, factor them, or expand to the factors, and then solve for s. So it's some algebra. I trust that you can all do it. For the sake of time, I'm going to skip ahead and say this results in s equals ks times 1 plus theta kd divided by theta mu max minus 1 minus theta kd. Okay, so that gives us a way to solve for s. In terms of these parameters, we can solve for theta because we know the flow rate and we know the size of the pond. We're given default values for ks and mu max and kd. So we can just put all the numbers in, and if we do use the defaults and solve for theta, we should get s equals 6.9 milligrams BOD per liter. So I'm going to give you this equation on your formula sheet, but keep in mind this is specifically for the pond scenario. The pond scenario where you have no influent x, right? So I'm not wanting you to go through this entire process if you get a pond scenario situation. And the reason I'm giving you this and the pond is relevant is because this is kind of a simplified version of the wastewater treatment process, right? We have bacteria growing in a system, a stirred system. So bacteria is growing and therefore substrate's being used and then it's going out, right? So it makes some sense that you'd have this understanding. It turns out that for the other systems, we'll look at it next time, but we're not going to go to the same level of mass balances for the recycled system. We have, in essence, it's kind of like shortcuts to deal with them a little on a simpler manner. Okay, but at least we know that the principles we've learned so far in the class can get us to an answer here for this case in particular. Okay, so then part B says what's that efficiency? That's simply going to be S naught minus the S we resulted in divided by S naught times 100%. So pretty standard efficiency. That'll be 95 minus 6.9 divided by 95 times 100% should be 92.7%. Okay, so the pond itself did a pretty good job at it given these conditions. So kind of makes sense that a wastewater stabilization lagoon, which is an engineered pond, can do a decent job. So we had an inflow concentration of 95 milligrams per liter there. Okay, so then part C, if we did a mass balance on X to find S, well, it turns out mass balance on S can give us X. Okay, so counterintuitive here, but this is the way it's going to work. So X equals what? So we do a mass balance on S. All right, so if we do that, we can start off and say 0 is equal to QS naught minus QS. And then here, all we need is the substrate utilization rate in that volume. And I kind of wrote some of this up earlier, but the substrate utilization rate can be put in terms of the growth rate, right? So if we have minus RG over Y, so it's the amount of growth divided by the yield coefficient, that's where we get our substrate utilization. We know that. We know, of course, R of G is mu times X. So we can put that there. And I'll go ahead and expand it. And I'm going to say R for the substrate utilization then is negative mu times X. I'm going to take the X first and then say this is going to be mu max S divided by Ks plus S. That's mu. Divide all that by Y. And Y, if we remember, was the mu max divided by that other K, that maximum substrate utilization rate, K. K by itself, lowercase k. All right, so with that, we can simplify a little bit. The mu's will cancel, mu maxes will cancel rather. So substrate utilization rate then becomes negative X lowercase k by itself times S. So that's not Ks, that is K times S. Sorry for the confusion. Divided by Ks plus S. Okay, like I said, annoying that there are so many Ks here, but we'll take that then and put it into our mass balance here. And then we'll be able to solve because we have X here that we're trying to solve for, and we already know S because we solved for S earlier. Okay. So we can continue then and say 0 equals QS, Q S naught minus QS. And this is going to be a minus VX. Let's put it up here. X lowercase k times S divided by Ks plus S. And from here, we need to solve for X. So we'll go ahead and add the V, this term on the right to both sides. We'll say VX KS over KS plus S equals Q S naught minus Q S. And essentially from here, we're going to simplify and solve for X, right? So if we divide both sides by, well, let's say we'll multiply first by the Ks plus S. So we have VX KS equals, let's see how I did in my notes. All right. Well, I've deviated a little bit from the notes I had from last time, so we'll just do it manually. Let me know if I did something wrong, if you see something. We can factor out the Q here and then divide everything by Q, and then V over Q will give us a theta. So maybe we'll do that in a moment. For now, let's just say divide the stuff accordingly to get to the X. So I'm going to say, probably right here. X then is equal to Q. I'm going to go ahead and factor it out a little bit here. S naught minus S. KS plus S. All that divided by this V, K, and S. So the Q over V, that's 1 over theta. So we could put a theta on the bottom. So I'll go ahead and divide the top and the bottom by Q. So V over Q becomes theta. Okay. Okay, so then we have that term as well. This is the microbe concentration in a CSTR at steady state given these conditions. So we can use that, put in the numbers we know. Also going to give you this equation on the formula sheet, but again, this is the pond equation. That gives us an answer of 43 milligrams per liter of VSS. Okay, does that make some sense? A little bit. So if I were to give you a pond problem, already giving you these equations, the x equals this stuff, s equals this stuff, my hope is that you could manage to answer some questions like, what is the BOD? Leaving the pond, what's remaining? Perhaps some add-ons to this to be able to manipulate that type of a problem, understanding where these equations are corresponding. You have a question? All right, so next time we'll get into what happens when we have recycle and what does that do to our kind of management, how our waste activated sludge line helps dictate the overall microbes in the system. All right, so with that, I'll see you guys on Tuesday.